chapters 5 and 6 contain a lot of information. And personally, I like to make brainstorm maps, or however you want to call it, where I just kind of write out in a big blob what is going on for each topic in a chapter. So I just wanted to make a short video kind of as a how-to and also as a review method for chapters 5 and 6 of General Chemistry 1. So I'll always start by just writing out chapter 5, chapter 6, whatever you're doing. I'll just put it in the middle of my screen here. And I'm just going to start making arrows off to the different things in chapter 5. And the first thing I'm going to do is I'm going to talk about energy, where delta E equals Q plus W, where Q is heat into the system and W is work on the system, or work done on the system. We can draw this as a diagram right here. Just blow it up. This right here is our system. We're going to have arrows into the system. We're going to have arrows coming out of the system. These top arrows are going to be Q. These bottom arrows are going to be W. And we're just going to label them as such, right? So this Q is going to be heat into the system. This W is going to be work done on the system. The Q on the top on the other side, so I'm sure you can imagine, right, would be heat out of the system. And this W would actually be work done by the system, right? The blue arrows involve the energy of the system increasing. The red arrows involve the energy of the system decreasing. So that is pretty much the component for energy, right? Undo, sorry. And one last thing, remember that when we're talking about heat flow, heat flows from hot to cold. And I'll just make a better arrow there. Actually, I'm going to write it right here. Right, so more concentrated to less concentrated. This is very similar to diffusion if you're a biology person. So something else I want to talk about is kind of like E, but it's Q. Right? There's two equations for Q. One equation is Q, which is the heat, equals NCP delta T. And there's a second equation for Q, where Q equals MCS delta T. And these two equations essentially mean the same thing, right? So remembering that our Q in both situations is our heat in joules. In this case, our N is the number of moles of whatever is being heated, or is taking in the heat or releasing the heat. Make sure you're using that in context again. Make that a little more. There it is. Right, and then CP, right, is, so C sub P, right, is our specific heat, right, but it's our molar enthalpy, right? So if we solve for CP, the units on CP will be heat in, specific heat in joules per mole degrees Celsius, right? That is because we have moles over here, degrees Celsius over here, joules over here. So this cancels out the units, right? Leaves joules so that we can actually solve for our heat. Delta T, remember, is T final minus T initial. If that's a negative number, that's okay. That is totally okay. Okay? Now moving down to the other equation, right? This M here is the mass of whatever is being heated. Right? This CS is the specific heat in joules per gram degrees Celsius. Why? Because instead of moles, we have grams, right? And usually grams, you know, you might see a different one. If you do, unit conversions are your friend. Again, delta T equals T final minus T initial. Sorry. So, we have one more big topic to do. And these, again, this is just a very general, very abbreviated Chapter 5 overview, so really hitting the highlights. There's one more thing that we need to talk about, and we need to talk about enthalpy of reaction. Now remember, for your intents and purposes right now, enthalpy, energy, same deal. Okay? Enthalpy and energy, same thing. Remember, you'll be given, right? You'll be given a reaction, you'll be given standard enthalpies, and you will have to figure out the enthalpy of reaction, or delta H reaction, as we say. And there's two things to talk about this. We'll talk about delta H reaction, and we'll talk about Hess's law along with that. So what I'm going to do is I'm just going to make this arrow. Actually, I'm going to make it smaller so I have more room to write. So let's just say we have the reaction A plus 3B yields 2C plus 5D. Right? And again, I'm just throwing numbers and letters in there. We're just going to do a quick example question. Right? And I want you to find the delta H reaction. So I'm going to give you delta H standard values. Right? So I'm going to say, I'm not going to write delta H standard every time. I'm just going to assume we're doing it. So let's just say that A is 5 joules, B is 12 joules. Now let's go 15. C is negative 10 joules, and D is 10 joules. So just picking arbitrary numbers here. Remember that our delta H reaction equals the delta H of the products minus the delta H of the reactants, right? So again, just to touch on it, these right here are the reactants, and these right here are the products. So, we're going to do this just as a normal sample problem, right? Let's write out, right, delta H reaction equals, right? So we're going to start with products. But we can't just take these numbers and plug them in for one equivalent of each, right? Because some of these chemical species, as we're calling them, have coefficients, right? There's 2 moles of C for every 3 moles of B, right? For every 1 mole of A, there's 2 moles of C, 5 moles of D. There's molar ratios we have to worry about. And it turns out that we multiply the standard enthalpies standard enthalpies by those reaction coefficients or mole ratios to obtain the proper ratio of the abundance of these items and to therefore calculate the correct delta H reaction. So delta H reaction in this case is going to equal 2 times delta HC plus 5 times delta HD. And I'm going to write it vertically just so you can see it. But I'll write this horizontally for the rest of it. I just ran out of room. Minus, right, delta HA plus 3 delta HB. Right? Important that you remember it's products minus reactants. This can be a positive number, it can be a negative number. We'll find out once we do the problem, right? So let's do the problem. Delta H reaction equals 2 times, right? And then we're going to go over, find C, negative 10 joules plus 5 times 10 joules minus 5 joules plus 3 times 15 joules. All right. We can just take, we can take these and these, right? So 2 times negative 10 is negative 20, plus 50 is positive 30 joules. And I just wrote that plus there just to remind myself that it's positive. Oftentimes with delta H reaction, we work with negative numbers as well. Remember that if delta H reaction is greater than 0, the reaction is endothermic. If delta H reaction is less than 0, the reaction is exothermic. So we just go back. So we have our positive 30 joules minus, right, and then we're going to have our 5 joules plus 3 times 15 joules, right? So that altogether is going to be 50 joules. Right, and that's positive 50. So positive 30 minus positive 50 equals negative 20 joules. And that is how we would go about a delta H reaction problem, right? And I'm just going to write this down really quick. Delta H is less than 0. Exo. Delta H is greater than 0. Endo. Right. So one more thing that we need to talk about is Hess's law. Sure, we can make another color for that. So we'll go right here. I'm gonna write that higher up. So Hess's law, right? If you have been through algebra already, you'll remember that there's 2 ways to solve a system of equations. There's substitution and elimination, right? This is the elimination system of equation solving method of chemistry, right? You want to get everything you don't need to cancel out so you can solve for what you want. We're just going to do a very simple Hess's law question. So what we are able to do is we can go about it and solve it. So, let's just take a simple reaction problem, and we're really going to go for a basic version. We are going to go for this. So I'm going to give you a parent reaction. You're always going to have a parent reaction. So, and you're always going to be finding delta H reaction, right? And here's the reaction. Here it comes. C2H4 plus H2 yields C2H6. I'm going to leave the states off for right now. Sometimes it just makes it a little bit messy. I want to make this as clear as possible. So the three reactions we have to work with are these three, and I will give you delta H's for them as well. I'm just going to zoom in on this for you. Right, so here's number one. Right, we have C2H4 plus 3O2 yields 2CO2 plus 2H2O. If you recall from chapter 4, that's a combustion reaction. And the delta H for that reaction is negative 1,411 kilojoules. The next reaction that we're going to do is C2H6 plus 3.5 O2, so 7 halves O2. Remember, you can have fractions in Hess's law equations. Yields 2CO2 plus 3H2O. Last equation that we're going to use is going to be some water synthesis, right? So H2 plus half O2 yields H2O. Now, there's a lot of ways that you can go about Hess's law questions. And personally, I try to just put the reactants and products on the right sides so that at least I can start canceling out the things that need to go. So when you look at your parent reaction, right, you need to identify the reactants and products that you need to keep. Right? So I need a C2H4 on the reactant side, I need an H2 on the reactant side, and I need C2H6 on the product side, right? So the first step I'm going to say is, can I find a C2H4? Yes. And is it on the reactant side? Yes, right? So at the moment, I don't need to do anything to this equation. I have C2H4. I have exactly what I need, right? So now, right, I'm not going to do anything to this equation. I'm going to leave it alone. If it doesn't cause problems. Right? So now, since I know that I'm not having to do anything to the first equation, right, what do I have to do to the second equation? What is happening right now? Boom. Point. Sorry. Sometimes this app is functional and sometimes it just craps out on me. It happens. So the next thing I need to find is I need an H2 that's on the reactant side. Do I have an H2 on the reactant side? Turns out I do. Last thing I need is a C2H6 on the product side. Now, this is going to pose a problem because these are all combustion reactions, right? Fuel, oxygen, giving carbon dioxide and water, or in this case, just the synthesis reaction for water. I need this C2H6 to be on the product side. So I get that to go to the product side by multiplying this whole equation by -1 and the delta H by -1. Now, the reason I'm doing this is because when I do this, right, what were the products become the reactants, what were the reactants become the products, and now I have a C2H6 on the product side, right? So since this is over here, then this is technically on the right side of the equation, right? So I'm actually going to rewrite equation 2, and I'm going to call it just 2 prime, right? 2CO2 plus 3H2O yields C2H6 plus 7 halves O2, right? So now I've multiplied by -1. Now I'm not going to erase my work. I'm going to leave this because it is good to show how you made these conclusions, right? So now I'm going to say, what's the last thing I need? Well, I have done everything that I need. So the last step is to make sure that everything actually cancels out as you want it to, right? So the only things that should be left are C2H4 and H2 on the reactant side. I didn't realize how messy that was. C2H4 on the reactant side and H2 on the reactant side and C2H6 on the product side, right? So I have a C2H4 here. It's the only C2H4 in this entire system, right? So I don't need to do anything to that, right? Now, I have 3 O2s over here, and I don't want those. What I'm going to do is I'm going to be sneaky, right? So we're adding these up. Technically, what's happening, I'm not really being sneaky. Remember, we're adding these up. We're adding up the delta H's, right? So what do we have, right? We have our C2H4, we're good, right? We have our C2H6 over here, we're good. But we have all this other stuff that we don't want, right? Now, altogether, we have 3 oxygens in the first equation and 1/2 of an oxygen molecule in the last equation. 3 oxygen molecules is like 6 halves, right? So 6 halves plus 1/2 is 7 halves, right? So the oxygens cancel out. How convenient, right? We flip that second equation and suddenly now our oxygens go away. So let's see if the same thing happens with our carbon dioxides, right? See if the same thing happens. Right, so we find our first carbon dioxide, we work our way down, it's in equation 1, it's a product, right? We want those to cancel. So we need to find 2 CO2 that appears in another place, and it turns out it's a reactant in the flipped second equation. So the carbon dioxides go away. Last thing we need to get rid of is these pesky waters, and it turns out you're going to do this the same way that you got rid of the O2s, right? Your first equation has 2 waters, your third equation has 1 water, your flipped second equation has 3 waters. Equations 1 and 3 have water as a product, as for a total of 3 H2O on the product side. The flipped equation 2 has 3 H2O on the reactant side. So your waters go away. Right? I like to, when I am doing these problems, and especially when I was in general chemistry 1, I liked to box out the things that I didn't cross out to make sure that I had everything that I needed. Right? I need C2H4, I have C2H4. I need H2, I have H2. I need C2H6, I have C2H6. So when we add up the reaction, we get C2H4 plus H2 yields C2H6. Right? That matches the reaction that we had written down initially. So now all we have to do is add up our delta H's. Now, word to the wise, I wrote this in kind of gut reaction. I'm used to just showing all my work in all situations. When you flip a reaction, okay, if we had one of these that we'd have to multiply by 2, anything that happens, you have to perform the same operation on the delta H so that we can get the correct value. So in this case, right, delta H reaction equals negative 1411 kilojoules plus, sorry, that was a little bit obnoxious. So new delta H, positive 1560 kilojoules for that flipped reaction. So plus 1560 kilojoules plus negative 285.8 kilojoules, right? And then you will get your delta H reaction to equal out to negative 137 kilojoules. So that's how I like to write these things out and do it. Obviously, you don't need to do all those steps if you don't want to, but that was just to show you that there's multiple ways of doing it. So that is a really big brainstorm of the contents of Chapter 5. and I encourage you to apply these techniques to further chapters, and best of luck.